let's see how this behaves. So we do our loop VB minus, and then when we go across the inductor, remember the definition of L is negative EMF over di dt. So the voltage across the inductor is going to be negative L di dt. By definition, that is the definition of inductance, is the EMF over di dt. So then the voltage drop across the inductor is going to be this one cross multiplies over there. You'll get negative L di dt. So negative L di dt, and then negative, and then you lose another voltage across the resistor, IR, and that's equal to 0. And then you're going to have L di dt plus IR. Well, if you remember, that kind of looks like the differential equation that we got for RC circuit, right? For RC circuit, what was it? VB, resistor, capacitor, then we had VB minus IR minus Q over C is 0. Then we had VB was dq dt R plus 1 over CQ. So it looks different, but it's again a linear differential equation with first order, right? dq dt. So the derivative of a function plus the function must equal to a constant. And what was the solution to that? Remember, it was Q A e to the minus, what was the general solution? T minus T over, you know what, we could just do it again. dt plus d. So we could just repeat this one. And then once we know how to do this one, if something looks the same, then we just basically replace the variables. So dq dt, negative a b e to the minus bt. Then we put it into here, or negative ab e to the minus bt plus 1 over c, and then q. Then we distribute the c, negative RAB plus a over c e to the minus bt plus d over c. So remember, the next step we did, we chose the function that could satisfy that kind of differential equation. Then we took its derivative. Then we put the derivative into this function, and then the q into that function. Then we distribute this. Then we say this needs to equal 0, because for all values of t, this whole thing needs to equal to VB. So the coefficient of this guy, so negative rad plus a over c needs to equal 0, and then the a cancel. And what are we solving for here? Oh, we're solving for what d needs to equal. So we get 1 over c is equal to rb, and then b needs to equal 1 over rc. So then that replaces that. A e to the minus t over rc. And then d needs to equal VB CVB. D needs to equal CVB. C A e to the minus t or RC CVB. So that's the general solution of that kind of differential equation. So this constant here is called the time constant, right? The time constant of the RC circuit. And it must have units of seconds because second over second has to cancel. Okay, now how do we get A? Then we apply something known as what? It starts with the letter I. And then N. And then I. And then T. How many letters do I have to give? Come on. And then I. And then A. Anyone? One letter left. Oh, good job. Salvador guessed it. Initial conditions. Yeah. Right. Good job, Salvador. You got the last letter. Okay, so if the capacitor is uncharged, then you say Q of 0 is 0. Then you solve for A that way. So this is the more general one because you could take care of if the charge is initially positive, then you could take care of that. If the charge is initially negative, you could take care of that. You see? So then that would be, this is probably better to remember because it takes care of if the charge is not initially 0, right? Same thing with the inductor. I could have an inductor whose magnetic field, whose initial voltage, let's say it's initially charged so that it has magnetic field this way, or it has magnetic field the other way. You see? So it could be either this way or this way. So we could have an initial condition other than 0 necessarily. So it'd be nice to know the general equation. Then you could say if Q of 0 is 0, then you can apply the initial condition. Then you could say 0 is A e to the 0 plus CVB. And then A is going to be equal to negative CVB. And then you could put your negative CVB, e to the minus T over RC plus CVB. And then you could factor out the CVB. Then you have the case where it initially starts with 0 charge, right? So you could kind of do anything. You could have a negative initial charge or a positive initial charge on the capacitor. Okay, so now if we look here, all we have to do is just really replace variables. So Q is replaced by I. So however Q acts in this case, the current in this case behaves like the Q in this case, right? Oh, by the way, once you get the Q in the RC circuit, the I is going to be the derivative of the Q. So you first solve for the Q, right? And then the derivative dQ dt is going to be the current in the circuit. So then it's going to be the derivative of this guy, which is going to be 1 over RC. And then the C and C cancels. Okay. So then the charge of an RC circuit, the charge of the capacitor charges asymptotically until it reaches CVB, right? And then the current starts out high in an RC circuit, and then decays. So it starts at VB over R, and then decays like this asymptotically. So in other words, for an RC circuit, it takes a while for the charge of the capacitor to build up. So initially the current is at its highest. The current flows unimpeded. But eventually, as the charge of the capacitor builds up positive charge here and negative charge there, right? Then eventually the capacitor kind of kills the current and stops it from flowing, right, in the RC circuit. But now let's see how the LR circuit is going to behave. In the LR circuit, the current will behave like the charge of the capacitor, right? And then the rate of change of the current is going to behave like the current, you see? So then the solution to this equation is going to be what? Let's see here. So the I is going to be I of t, and then you're going to have here, so instead of Q, you replace Q by I. So the current in a LR circuit will be this kind of a function. And then what's going to be the, well, let's write for a second, let's just write plus D. Okay, then what's going to be the, what's going to be the B? In our case, B was 1 over RC, right? So it was, in a sense, it was whatever was down here times there, that was the time constant. The time constant was 1 over RC. So in our case, what is it going to be? Well, there's nothing really down here, you see, but we could write this like this. L di dt. So you see L is acting like the R, and then you have 1 over R. 1 over R I. So you see I brought the R so that it's in the denominator as a 1 over R. So then my C is being replaced by 1 over R, you see? And my R is being replaced by L, you see? So it's just, these are just variables. So I can just say the solution is going to be the exact same thing. So what's going to be my B then? B is going to be 1 over R is being replaced. R was where? R was here. So R is being replaced by L, right? 1 over L. And then C is being replaced by what? 1 over R. You see? C is being replaced 1 over R. Okay, so then D is equal to R over L. So then L over R. Yeah, so then that's going to be units of ohms, seconds over ohm. And then ohm cancel. Yeah, then that's seconds. Yeah. So the time constant is L over R. So then the R would come down to the bottom and the time constant would be written on the bottom. You see. So then you have your VB over R, 1 minus e to the minus L over R on the bottom. Okay, so the derivative would be VB over R, 1 over L over R, and then you have di dt is equal to R cancel, BB over L, e to the minus t over, this is L over R. L over R. So it looks like this kind of a function. Okay. So now you can kind of see how the LR circuit is behaving opposite to the RC circuit. Let's try to see why. as soon as you connect, as soon as you close the circuit here, what's happening? This one is telling you as soon as you close the circuit, the rate of change of the current is very high in the circuit because you're all of a sudden introducing a battery into the circuit, right? The rate of change of the current is high. When the rate of the change of the current is high, the inductor opposes the circuit a lot, right? Initially, it doesn't want a new introduction of a current and a new introduction of a magnetic field. So the back EMF is very strong. And so initially it kills, the inductor kills the voltage of the battery, and therefore the initial current is zero. You see, the initial current in the circuit is zero. But now, as time goes on, the rate of change of the current is dropping, you see. And therefore, the inductor is easing back on you and allowing more and more current to flow, you see. And then eventually, towards the end, it's as if the inductor doesn't exist in the circuit. And so at that point, the current in the circuit flows unimpeded. Opposite of the capacitor, you see. The capacitor initially is uncharged, and therefore it allows the complete unimpedance of current. The current flows unimpeded. But eventually, as the capacitor gets charged, it kills the current and the current dies. But here, the initial current is zero. So inductor is more killing the circuit at the beginning, right? At the beginning, when you're first introducing the battery, the inductor is saying, oh, no, 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 right? But the capacitor is killing the current at the end, after you have already charged it. Do you see? You get that, Daniel? Looks good. So let's now talk a little bit about what are the physics 101 equivalents of an inductor, a resistor, and a capacitor. Each one has a mechanics equivalent, right? What's the equivalent of an inductor? What's the equivalent of a resistor? What's the equivalent of a capacitor? Once you begin understanding that, the picture starts making so beautiful sense. So think about the equation. The EMF of an inductor is L di dt. Forget about the negative for now. The EMF of a resistor is resistance times current. And the EMF of a capacitor is equal to 1 over C times the current, the charge. Okay. So the physics 101 equivalent of each of this would be force is equal to MA. So force takes the place of voltage. Remember, EMF is electromotive force. It's anything that drives current. So for mechanical force replaces EMF. Mass replaces inductance. And A is di dt. So A is dV dt, right? M dV dt. So the mechanical equivalent of an inductor is something that has mass, which has inertia. You see? So inductor is to mass. You see? So then what replaces this guy? F is equal to, in physics 101, we have air friction, BV. Air friction is linearly proportional to velocity, right? So V is to I as force is to EMF of a resistor. Air friction coefficient is analogous to resistance of a resistor. So resistance is to air friction. Okay, this is air friction coefficient. We can call this air drag. Air drag. Okay, now what replaces this? Force. Q is replaced by X. Okay, and then 1 over C is replaced by Hooke's law, the constant K of Hooke's law. What is that called? The spring constant of the spring, right? So therefore, 1 over capacitance is replaced by the Hooke's law. This is spring constant. And this is inertial mass. Inertial mass. Okay, so if I want to analyze any physics 1 problem that is similar to a physics 3 problem or physics 102 problem, right? Then we can kind of analyze them similarly. So we can say, what's the equivalent of a charging RC circuit? RC. Okay, a battery is like having gravity, right? A resistor is like having air friction, and a capacitor is like having a spring. So the physics 101 equivalent of this problem would be take a wall, hang a spring from a wall, and analyze what's going to happen, because gravity is going to cause the spring to the gravity is going to cause the spring to stretch, right? And then air friction is going to affect the spring, and then eventually the spring will stretch and then come to a stop, right? So if I want to graph the position of the spring as a function of time, and if I want to graph the velocity of the spring as a function of time, how do I do it? Well, I can cheat and I can say the position of the spring as a function of time will behave like the charge of the capacitor as a function of time. You see? Position is to charge. You see? Position is to charge. And then the velocity of the spring as a function of time will behave like the current in the circuit. You see? So this is what you're doing, is you're using analogies so that you don't have to do the work all over again, right? So how did the charge of this guy behave? Well, we have a graph for it right here, right? So let's redraw that here. The charge of the capacitor builds up, builds up, builds up until it reaches CVB, right? The current in the circuit starts out at VB over R and then drops to 0. That's in a charging RC circuit, right? Okay. Now let's see how that we can translate that to this problem, physics 101 problem, right? So then the position of the spring, right? The position of the spring, in other words, the stretch amount. The spring will stretch, right? So the stretch will start at 0, and it's gonna increase, increase, increase until it reaches what? What replaces VB? What replaces C? Right? So VB is the voltage of the battery. It's replaced by the gravitational mass, the gravitational weight of the spring. So VB is replaced by mg. You see? The weight of the spring. And then C is replaced by what? 1 over the constant, the Hooke's constant. There you have it. So in other words, the spring will stretch until the edge of the spring has stretched by an amount mg over k. Does that make sense? Yeah. The mg is the weight of the spring, and you divide that by the spring constant of the spring, and that gives you the stretch amount of the spring. Isn't that weird? So you're talking RC circuit and RC circuit, they're the same thing. Spring and the gravity. Okay. Then the velocity of the spring is going to do what? VB is going to be mg. This is the velocity of the spring. VB is going to be mg. And then you divide by the resistance, so you divide by the air friction. So the initial velocity that the spring is dropping is equal to its weight divided by the air friction constant, right? So that's going to be the initial velocity. And then eventually the velocity, as it goes down, the velocity is going to go all the way to 0, and then it's going to stop asymptotically. Stop, go like that, stop. What's going to be the time constant? The time constant of that circuit. Well, in a spring, for a RC circuit, it's RC, right? So what's the time constant of this? You replace R by the air friction, B, and then you replace C by 1 over K. B over K. So that means in a time equal to whatever the air friction is, divided by K, it will have already stretched, the spring will have stretched to 63% of its maximum stretch amount. So something like right around here. Do you see? So you can kind of see this a little bit more than this, because this isn't, you know, physics 102 is not very visual, whereas physics 101, they're more visual problems. You say, oh, I see. So the stretch amount that this is the equivalent of how much this is being charged. You see that? So that's the powerful tool, is that you're replacing something that you can't see with something that you can see. And you're saying, oh, okay. And then in one time constant, what's happening? The velocity of the spring is going to 37%. So initially it drops down very fast. And then by the time it gets here, it's going 37% of its initial velocity. And then eventually when it gets down here, the spring stops. You see? And then it ends right there. So that would be the equivalent of the RC circuit, would be a spring, some air friction, and gravity. You see? Okay, now what would be the equivalent of the LR circuit? So if we have the LR circuit is a little bit even harder to visualize, right? Because we just learned inductance. We don't really have a good grasp of what inductance is. So now this is physics where physics 101 can come even more handy. We can say, oh, okay, so here L, R. So now how are things behaving? Here, the current is the one that's starting at 0. And it's going like this, right? I'm just redrawing what we did earlier. And then what's the time constant? L over R, right? Yeah, L over R. So L over R. Okay, and then the derivative of the current is behaving like the current in the RC circuit. So starting high, starting at VB over L, and then it drops to 0. You see, we have less grasp of this because we haven't really dealt and done too many problems with inductance. But let's see if the Physics 101 equivalent will help us. So what does it mean to say we have an inductor and a resistor and gravity? This is gravity. So that would be like taking an object from a certain height. Remember, inductor is like mass, right? So if you take an object from a certain height and then drop it under the influence of air friction, that's it. No spring. There's no capacitor here. That's it. So drop that object and then analyze what's going to happen to it. If you remember, Daniel, we did this in Physics 101, right? The motion of an object under the influence of air friction, we saw that the initial velocity starts out high, but then as it's going faster, air friction starts increasing, and then eventually it asymptotically reaches something called terminal velocity, right? So that means the velocity of this should act like the current of this guy. You see, I is to V. And that is actually what we saw back in Physics 101. The velocity starts at 0, it asymptotically goes up. And if you remember, the equation of the terminal velocity was what? mg over b. That's the terminal velocity under the influence of air friction. So let's see if that works. You see, you're replacing vb by mg and r by b. Cool. Wow, that's exciting. So you can kind of think of this as terminal current, right? The terminal current in an LR circuit. So that's terminal velocity. And then the time constant, in Physics 101, we don't really talk about time constant. But you could, nothing prevents you from doing that. You could say the time constant is the time for the velocity of a ball to reach 63% of its maximum velocity, right? So 63% of its Vmax, or terminal velocity, right? So what would the time constant be? M over B. There you have it. And it would actually have units of seconds. The units would work out. Okay, and then therefore, the di dt is going to be what? The derivative of v, which is going to be a. So the acceleration of an object starts out actually high. Oh, you see, that makes sense. When I first drop an object, there is no air friction on it yet. So it should have its maximum acceleration, right? Then as it falls, the acceleration should reach 0 asymptotically. There you have it. The rate of change of current is like acceleration. So then what's the initial acceleration? Vb over L. What's Vb? Vb gets replaced by mg. L gets replaced by m. I don't know why. I love that. So mg over m, and then what happens? This cancels. The initial acceleration is g. Okay, then it goes, drops down, and then the time constant is the same, m over b. Now, usually in Physics 101, we also plot the y. In other words, the position of the block, right? How far it has traveled. So then the y graph would be the integral of the v. In other words, you would go back and graph the y. And then what was the equation for that? If you remember, I don't know if you remember, that was the equation for the position of an object under the influence of air friction, right? So we have to go back to our Physics 101 Kiledjian.elac.org. This is my old website. So Physics 1 and test 3 formulas. Okay, yeah, you see there? This is the equation for the acceleration for under air friction, velocity, and now this is position as a function of. So I could write that equation down. Y of t mg over b, t plus m over b, e to the minus bt over m, minus m over b. Now, could I cheat and go back and now do this for electricity just by copying? Is that allowed? Yeah? In other words, if I know the position of this function, it's going to look something like this. So the position of an object under the influence of air friction is just going to keep going. And if there's no ground to hit, it will just go forever. So, you know, it's not like this one where the position of the spring, naturally it stretches, but then eventually it doesn't stretch anymore. It's not like that, where it stretches and reaches a maximum stretch. If there's no spring, the block will just go forever. Do you see? And it's just going to go forever. Well, what does that mean? What's position similar in LR circuit? Then that's the integral of y, right? Which is going to be Q. So how should the Q behave here? The charge that the battery is sending to the LR circuit. Well, it should never have a maximum because you're not charging the capacitor here. So the battery is just going to keep sending charge forever, you know. So what is the charge going to look like? Similar to the position of a falling body under the influence of air friction. So let's write that on another page. This is so amazing. Oh man. Q. So y of t was mg over b, t plus m over b, e to the minus bt over m, minus m over b. Right, so then if I were to replace this by their electrical equivalents, what would I do? Q of t is VB over R T plus L over R e to the minus RT over L minus L over R. So the charge is going to just go like this, and forever it will just keep charging, right? It will just keep charging forever. Let's see here. So what's going to happen as t goes to very large values? Limit as t goes to infinity, q of t. This portion of the function is going to disappear, and you're just going to have VB over R t for very large values of t. And this is going to be negligible, so you're just going to have t. In other words, as the function, as you go to larger and larger values of t, this function becomes linear, proportional to t. Why is that? Well, what did we see for the inductor? When you close the circuit, that's when the inductor first really acts towards you, against you, right? Because it doesn't like changes of current. So when you close it, the inductor really resists. But after a while, the inductor says, that's fine, I'm okay, the current can keep flowing. So way when you're at very long times, is as if you don't have an inductor at all. You just have the battery. You just have the battery charging sending charge through the resistor, just IR, right? So the charge that the battery is sending is literally just the voltage of the battery divided by the resistance of the resistor. That's equal to the current, right, times T. In other words, at the end, whatever the current in the circuit is, right, the current is just going to equal the voltage of the battery of the resistor, because the inductor is going to act as if it's not even there at the end. You see? So then you just take the current and you multiply by time, and that gives you the charge that the battery sends, and it never plateaus. It never reaches a maximum charge, you see? So that's why it behaves different than the charge of the capacitor. Okay, so now you can kind of see how the LR circuit behaves.